This is the Makespace How to Design Electronics. It's a monthly session, shall we say. It's online. We might bring it to Makespace at some point next year. COVID allows us. Really, these here are, it's about a half hour of me just talking about different things about different electronic subjects. If you have any questions, if anything's not clear, if you want me to go over anything again, by all means, just stop me and interrupt. I'm all for taking questions and interruptions. I will say, if you do have like a telephone call or something, just maybe remember to mute your microphone. I think last time we all enjoyed somebody else's conversation for a bit. And so, yeah, so this is just about giving you tips for your own electronics, really. So it's not about derivation. There's loads of stuff out there already. And so the topics which we've got, they're all going to be based around the main theme of microcontrollers for this season 2. And they're all subjects which essentially people have asked me about, you know, could I talk about this or that? So trying to do this a little bit for everybody. Right, I'm going to adjust this camera because I've only got one that's working. There we go. Right, there we go. So this is my opening slide, if you like. These slides are all available to download. There is a download. I've just printed it off here for us. So if you do want to download the slides, if the screen goes a bit funny, if you want to make any of your own notes, you can download all of these. They're all available. So that they're on there now. You can just go to that website and just scroll down to downloads, see documents, and you'll see a couple of links for last season and also for this season. Right, okay, so transistors, what are they? They are, I would say, the fundamental building block of all electronics. Now, I found this one, I just got it off the shelf. This is where they all started. This is a valve, can you believe? We're not going to play with the valve, but it came, when I bought it, it came in this absolutely enormous box. And it came with this enormous, amazing data sheet, inviting you to apply, if you can see it, but it actually does say 350 volts across these things. So these things back in the day, certainly before my time, were a little bit juicy. Yeah, you can see the sort of voltages they're suggesting you apply 300 volts RMS on some of these pins. Never actually wired one up. Maybe I will one day. But we don't play with these things these days. I went online and I looked for the biggest, baddest transistor I could find. And this was it. So this is still a little bit old school. They usually have a number of pins. We're going to talk about all these different pins and sort of things. What on earth do they mean? And so there's a couple of types of transistors that we are going to have a look at this evening. So there's two types here. So I've kind of categorized it here for everybody. So there are two types which I've got here. One's called bipolar junction, and they come in two flavors. And we'll have a little look at this one here called NPN. We'll talk about that. And then there's another flavor of transistor called the field effect transistor. And that comes in even more flavors. And we're going to have just a little look at some of them and where you can use them in, certainly in, if you're designing microcontroller systems, exactly just how useful are these things to us. So I thought the place we'd actually start would be with probably my favorite one, which is the bipolar transistor. So in electronics, we give them all symbols, and this is pretty much what they look like. It's got the 3 pins, just as we have here. This one's actually the case is one of the pins on these bigger ones. One's called the collector, one's called the base, and one's called the emitter. And you'll see there's always these little arrows. And these little arrows are always where the emitter is. And as you can see, this one's pointing out, and this one's pointing in. So that just tells us what sort of transistor we've got. And it's all about how you apply the voltage and whether it's a positive voltage or whether it's a negative voltage. That will determine what sort of these 2 transistors you want. And within these transistors, all sorts of things go on. This big one here is capable of handling 30 amps. If you're designing a small microcontroller, you might be talking 30 milliamps. So it's just horses for courses. And there are a couple of really good books I found. These are on Amazon. I'll point these out to you now. I found these on Amazon, these two books. They're £5 each. They're not bad. And some chap here, if you write down his name, Kavita Mara, if you just type that into Amazon, you'll find it pop up. They're £5 each. And there's loads and loads of background information in here. All about, some of the theories we haven't really got time to have a look at today, but there's loads and loads of background information on here. We'll have a tiny bit of a dig in. I mean, certainly the 2 transistors we've just been looking at, NPN and PNP, they tell you all about the breakdown of exactly how they're made and exactly how they work. Let's find a good picture here before we look at an application. Best picture's probably this one here, actually, one we opened with, where they just explain to just how they work. There's a ton of stuff on the internet. I haven't really got time this evening to dig into the theory of them. So what we want to have a look at is on how can I use them. So first top tip, £5 each, Amazon. You can't beat these. I think they're really good. I don't have shares or anything. So let's have a look at an application, a very simple one, shall we? So you can use these devices, these transistors, to amplify a signal. Now, all these transistors, these bipolar ones, they have a parameter called HFE. And that is the ratio between the current flowing into the collector and the current that will flow, it's meant to be B actually, I got that wrong, look at that. Into the base. So it's a gain. So if you were to want to say amplify a signal, this one here has a gain of say, I think it's about 60. So if you have a current gain, if you had a current gain of 60 and you put in say 1 milliamp, you'll get an increase through the collector of, if it's 60, it would be 60 milliamps. The limitation of using this kind of transistor for any sort of basic circuit is that this HFE parameter is a range, and different transistors will have a different range. This one here, these high power ones, usually have a very small gain. I think this one is typically, I think it's like 15 to 60. So it's quite a wide range. So if you were building an amplifier, then you'll be there forever trying to work, test your transistor to find out what its gain is before you could use it. So it works, but it's not really very reliable. It's all repeatable. So what do we do about that? Well, there is an answer, and it's quite easy. So it's a simple circuit here where the gain is actually just this resistor on the collector here divided by this value of this resistor here. And that works every time. So it's very simple transistor amplifier. And then these two resistors here are for biasing your signal. So what you generally try and do is you'll try and make that say this will say 5 volts. And if you'd make that say about 1 volt, which means you'd want that to be about 3 volts. So this could swing up and down from 5 volt to 1 volt, if that makes sense. So if that's 1 volt, you often end up with a voltage drop between, this was the base, and this was the collector, and this was the emitter. You tend to end up with about 0.7 of a volt there, which means the voltage across here is 1.7 volts. So you'd choose your potential divider circuit to give you a 1.7 volts, which would, at that point, which would give you about 1 volt at this point. And then the gain, depending on what your input here is, your V in, and this is your V out. Of course, V gain is V out with the V in, and that's the ratio of these two resistors. So that's a really simple transistor. In reality, I tend to use op-amps for amplification. Now on the input here, there's actually a capacitor. So this is a DC block. So you'd only want a small signal here, let's say plus or minus 0.1 of a volt. And if that was say 10 kilo ohms, that was 1 kilo ohm, gain of 10, then this would go say 3 volts up or down by 4 volts and 2 volts. You do see, when you look at these circuits, you do tend to see a capacitor on the output. But if you do that and then put it into your microcontroller, you'll be putting a negative voltage into the microcontroller, and that could cause a problem. So if you're going to experiment, I would probably say, whilst you see a lot of circuits with a capacitor on the output, leave the capacitor off, so you're only ever putting a positive voltage into your microcontroller. Or use an op-amp circuit. We talked about op-amps last year. If you have a dig back through the stuff online that we looked at last year, you'll see there's a whole session on op-amps and amplifiers. So that's one good use. What's a slightly more useful, maybe for using transistors, is to boost the power in your circuit. For example, an op-amp might generally have a maximum current output of just 30 milliamps. That wouldn't be unreasonable. But you might have a circuit that requires, let's say, 300 milliamps. You might be driving a speaker. So we can use a transistor again to boost the currents. Obviously make sure this transistor can deliver 300 milliamps, and that's just speccing it from looking at data sheets. And how this simple circuit works is there's always this voltage drop across here of 0.7 of a volt across there. So you'd want to make your reference voltage, well, let me rephrase this VREF here, whatever you wanted the voltage to be, the amplifier will make the output, it'll drive the output such that this is also at VREF. We'll call it VREF in a dash, which means that the voltage here is going to be VREF plus 0.7 of a volt, because that's what you lose across the base emitter of a transistor. So you'll never be able to have VREF at, say, the power supply and expect to see the power supply here, because you've always got to allow for a voltage drop. And if you're using, let's say, you want to create a voltage source in your circuit, this is a great way and a really easy way of doing it. So that you could have rather than having this fixed potential divider, if you've got a microcontroller, instead, we could get rid of that. And we could have this as the digital to analog converter output from your microcontroller. In fact, that wouldn't be a bad way of doing it at all. And then this would actually buffer it, and this would actually give you a nice, safe way of giving you a nice, clean output voltage. Any questions on those transistors? All very quiet. Always hope it's not me who's turned your microphones off. You can always put a question in the chat, so I'll hopefully pick them up afterwards.
It's okay.
Yeah, you can all hear me all okay? Yeah.
That's fine.
Yeah, always worry that I'm talking to myself. But as I say, you know, any questions, just stop me. I'm happy to go over anything again. In my view, I actually like it's called the BJT, the bipolar junction transistor. I personally find it a lot more interesting than the one we're going to look at next, which is the field effect transistor. These things are super duper cheap. You know, they can be cheap. I mean, they can range from a few pence up to a few pounds, you know, depending on how much power you want. And there's quite a lot of flavors of transistors, so we just can't go into them all here today. But in terms of what I use generally for electronic circuits, yeah, I will use the power boost here if I want to, certainly if I'm driving a digital to analog conversion output. So I do use that one quite a lot. And so if I'm doing amplification, I will admit I do tend to use op amps more than transistors, but since we're talking about transistors, we obviously need to include it, don't we? Right, okay, let's mosey along, shall we, a little bit, and let's have a look at the FET transistor, the field effect transistor. So again, it's got three legs, but they actually now gave them different names. Rather than collector, gate, and emitter, they've now called them drain, gate, and source. And again, there's two different types. One's called N channel, one's called P channel. And again, there's arrows, so you can work out, you know, whether it's an N channel or whether it's a P channel. With the FET transistors, if you remember at the beginning, maybe just go back to that one. There you see. So you can see they break down into quite a lot more. And there's a little bit more than this, but these are probably the more fundamental ones that you're more likely to be working with, shall we say. That side there. So they're the gates. Now I've got here that some of that enhancement and depletion. So I've color coded these to try and break them out a little bit. So we'll have a look in just a second of what does enhancement and depletion mean. Their symbols are very slightly different, as you can see. This one's got some broken lines in the middle here. This one hasn't. These ones here doesn't seem to have anything at all, but fundamentally, you can see there's a common way of that these are drawn compared to, let's go back to that one there, the common way that these ones are drawn. So it's quite easy to identify what's what. But what I do have here, this is my cheat sheet. I actually embed this often into my circuit diagrams. So you can think of a field effect transistor in many cases as an on-off switch. And that's what I tend to use them more for myself. And this GS means the voltage between the gate and the source. Plus V means it's positive between gate and source. If it's minus, then obviously it's the other way around. You'll probably find if it being minus, you'll probably say that might be, say, 10 volts, that might be 0 volts, that'd be a minus voltage. Or they might be tied together to ground, in which case that would be 0 volts. And depending on what you want, the way I start is what the gate source plus 0 and minus is going to be, and what function I want them to be doing, depending on what the gate source voltage is. The gate source being what's there. The gate source, write on for us, VGS. And depending on what I want from my table, we'll then decide what sort of transistor I'm going to want. And I always have this handy because I'll be honest, I can never remember this, is it an enhancement? Is it a depletion? Or an N channel? Or a P channel? So we'll have a look at a few of these in just a moment and where we can use them. But just draw a table and then decide which one you want, and then go shopping for the right transistor. So that's a great one to download and keep handy. That's my golden nugget for this evening is that one. Right, let's have a bit of a peek. I've got some applications here for us. Let's start with this one. So here's a fairly nice, straightforward one. Again, I tend to use this one quite a bit, the FET as a NOT gate. A NOT means the output is not the input. So if I might have this point here being driven by my microcontroller. If I was trying to control something, it's a good way to protect the microcontroller because it's cheaper to change a transistor than change a microcontroller. Or it's a NOT gate. So for example, with this one here, if I had, say, 5 volts here, then I might want this to turn on. So this is then say 5 volts, 0 volts. So then I want this to be on. So I want then this to be 0 volts. I think, right, which one of these transistors do I want? It looks like I'm going to want the N channel enhancement. Perfect. So I'll go and get, and that's what this ZXM61NO, it happens to be an N channel enhancement. And just as a quick tip, when you're looking at these transistors and circuits, they usually embed the type it is somewhere in the code. So you might find a ZXM61P02F. That would be its sibling of the same parameters, just a P channel FET instead. The other thing you can use these for is if you want to do any level shifting. Let's say, for example, we've got here the Arduino, which is the AVR. This one's on 5 volts. The ARM embed stuff, yeah, runs on, this is 3.3 volts. So what do I do? How do I get the signal from this chip to this chip? Well, here's a way to do it. So that one's there. So this is driving 5 volts. So if I make that 3 volts, as you can see, I've got a level shifter that I can communicate safely between the two chips and do the voltage conversion at the same time. Or I could do it the other way around, of course. I could very easily, this will rub out, which is nice. I could very easily, that could be my 3 volts. Yep, and that could be my 5 volts. So I can easily just do it the other way around. So often if I'm driving outputs on a circuit, rather than sending the pin straight to a port like this, I'll usually go through a transistor just to protect the chip from any potential damage. If you're doing R&D, playing around at MakeSpace, it probably doesn't matter. If you're designing a commercial product, I would definitely be putting this sort of protection on the board. Now, this is a NOT gate, so you could very easily, if you wanted, actually just drive another transistor. You can see here, with that 5 volts as well. There we go. That's the output. So if you wanted to, we could just, hopefully you can see that okay. If you wanted to, you could put another transistor on, and then the output would then just be exactly the same as the input, just at the alternative voltage. Easy peasy. This transistor here, resistor around this 10K resistor down here at the bottom. One thing worth remembering is if you're driving anything from a ARM chip or any microcontroller, I should say, when you put these chips into reset, the outputs usually will be floating, so there'll be a high impedance. They're neither a high voltage or a low voltage, and you wouldn't necessarily want your transistor then to have a unknown voltage. It's just not a good place to be. You want to be definitely know what you're doing. So if it's floating, say during reset, or if it's just unprogrammed, like when you buy a chip, pull down resistor or pull up, doesn't matter which, depends on your circuit, is a good way to be sure that your output is always going to be at a known state. Top tip. Right. Now then, this is one of my favorites next. This is a really good one. This is a good top tip. Often you'll see, certainly I think if you look at the Arduino circuit, they do this little trick, is to protect the circuit from the polarity being connected the wrong way round. Often you'll see circuits using a diode. Now, the trouble with the diode, of course, as you know, you've got a small voltage drop across. So if you had an input here, let's say this is your plus V in at the bottom, often you'll see a lot of circuits will put a diode in before, and that'll be 0 volts. That's our circuit there. So of course, a diode has a voltage drop of about 0.7 of a volts. So if you had 5 volts in, you'd only have 4.3 volts to control for your circuit. If that makes any sense. But the advantage, of course, is if you did accidentally, the pen that rubs out, it's brilliant. If you did accidentally get them the wrong way round, then you wouldn't go and damage your circuit because this diode would be in reverse and would protect the circuit. But there's a price, as we mentioned. And there's a way out of it. You can use an FET. This is a P channel transistor. The arrow's going out. And the gate is actually tied to ground, or 0 volts is often what we call ground. And so normally, if you plug everything the right way round, then the voltage drop across between the drain and the source is very close to 0 volts, which means your output will probably be very close to V in. So you don't get any voltage drop, or nothing worth writing home about. And if you were to put the polarity the wrong way round, so if this then was at 0 and this was at, say, plus V in, then the transistor switches off and protects the circuit. So in all of my circuits that I design, I always put in a MOSFET. And the one I've got here, this S17149 ADP, is one that I tend to use. It can handle something like 5 amps at least. So it's got good current capability. You don't get the voltage drop. And because it's a power transistor, it doesn't get hot either. So it's a win-win-win. It's a much better way of protecting your circuit than using a diode. The only thing I'll say, of course, is that it's certainly going to cost you a lot more than a diode, but you're going to at least have all the volts you want. And if you're designing something that runs on a battery, where the chances are of putting a battery in back to front is quite high, then certainly I'd be going for a MOSFET just to protect your circuit. And I'll be honest, I was doing at an EMC test site today, testing a circuit to help some people out. And I've been there 5 minutes and I put the battery on back to front. Was there any diode protection on it or a MOSFET? The answer is no. Did I get smoke out the board? Yes, I did. I've been there 5 minutes. Fortunately, I got away with it. Otherwise, today would have been an extremely short day. Had this sort of circuit, had this actually been on the circuit, then getting a wisp of smoke coming off the board wouldn't have happened. I got away with it. I was lucky. Right, what's the other thing with transistors? Yes, this might be one of the last things here actually for us this evening. Looking at it here, yeah. Okay, good half hour. Okay. Right, the other thing to use transistors for is controlling. It says actuator here. By an actuator, we mean something like a motor or a haptic motor. We'll talk about them in a second, actually. Something else I've discovered recently. So if you've got like a little buzzy motors, the sort of motor you have for vibrates in your mobile phone. So they can draw quite a bit of current, certainly to start. And they'll probably draw more current than any of these microcontrollers can deliver. So once again, just use a transistor just to switch on and off the, let's say it is a haptic motor, with a tiny motor with a little weight on the end, so you feel the vibration. And just another top tip, if you do that, don't forget to put a reverse diode into the circuit. The reason for these reverse diodes is if you think about a motor, if you remember your school day physics with I think it's Maxwell, isn't it? It's not Fleming, it's Maxwell. I think it's Maxwell's left hand and right hand rule. Does anyone remember that? Everyone goes, oh yeah, I remember something about that. Whereas if you have a motor, I can't remember who it was. Hang on, I do know because my physics teacher in Cambridge made a comment to me and it's stuck in my head. If you're making the current, so if you're spinning the motor to make current, it's the left-hand rule. And no, it's the right-hand rule. It's the right-hand rule if you're making, because my teacher said to me, it's a right-hand rule, but because you're left-handed, Stephen, you won't remember this. And I remembered that. So if you've got a motor and your fingers are the coil, and you want some motion, which is your thumb, which is called the right-hand rule, when the magnetic field collapses, the current goes the other way, which is the other hand. And so when the magnetic field collapses, the current will actually go the other way. And if you don't have a protection diode in there, its only path home is going to be through your transistor. And that will probably blow it up. So the way you solve it is you just put a diode in reverse across anything with a coil. Buzzers, for example, I tend to put one on. Little motors, I'll put one on. And this is an example here. I mean, just about any diode will do. This is a surface mount one, which I've been using recently for circuits. Like it says 0603. That means it's a surface mount device. But there's an absolute ton of them. Right, gosh, you know what? That kind of covers, that's a good half hour. Look at that. A brilliant timing on my part. Questions from anybody? Anyone like me to go over anything again?
Could you just switch back to one of the very early slides of the types again, please?
Yeah, of transistors or the MOSFETs?
Oh,
or both?
So
These are the transistors.
Yeah, no.
The other one?
The diagram that you had with the boxes.
Oh, okay. Yes. This one.
That's the one.
Yeah, I've color coded them to try and break it down. Yeah. What's the query?
I was just translating that into what you were just going through.
Oh, lovely. Okay. Yeah. Well, we can look at that again. Actually, we've got a bit of time. If anyone's got any questions or comments, I see the microphones are all off. I'm hoping that's not me that's done that. Let's see if I can. It's bizarre because the bit I have with everybody seems to have completely vanished. I know you can see my screen. But Deborah's on, so I'm assuming everyone's very politely turned their microphone off. So you're very welcome to chime in. Sorry, what was this? What did you say, Deb?
I was just going to flip from that screen. If you can just lift it up then again.
That, yeah, to
the diagram that's underneath.
This one, or this one.
This one, yeah.
This one. Okay, right. Okay. Well, look, got loads of time here. Yeah. So okay. So let's have a look. Well, what I would be inclined to do, Deborah, is rather than using this one. In fact, before I move on, I'll probably use the cheat sheet. But just before I move on to that, I have used an FET here, but there's no reason why you couldn't just use a bipolar transistor instead, which I'm sure people might be thinking. There's no reason, so I'll just draw it here next to it. So there's no reason why you couldn't actually control that from an NPN transistor instead. You might need to put a resistor in there. So there's no reason why you couldn't use an NPN transistor instead.
Can you label that up NPN? And
yes.
Then when we
NPN,
go back through.
Yeah,
through this,
and collector base emitter. And this is drain, gate, source. Yeah, that's just a quick point that you can use either whatever you've got to hand, whatever you've got most of on your circuit. So if you had a load of NPN transistors, in order to keep my unique components down, I would probably stick with an NPN. If I had MOSFETs everywhere, I'd probably stick with a MOSFET. So rather than just having too many unique components, I'll try and rationalize a little bit. But what I would tend to do in this case, Deborah and everybody else, if I find my cheat sheet, as I call it, here it is. I'll probably take my cheat sheet so we can work it out. So what do I want? Right, so when I've got on, we'll draw on this one. So I want to turn this motor on when I send a signal from my microcontroller. Let's say it's an ARM chip. Doesn't matter if it's ARM or AVR, doesn't matter. So when this is at 3.3 volts, I want this to turn on. Okay, for example. So the gate source, when that's positive, we want it on. So it looks like it's going to be that one or that one. It's going to be what I want. Yep.
Yeah.
So, and when it's at 0 volts, it's at 0 volts. I want this to be off. I want this device to be off. So like a switch. So it's at 0 volts. I want it to be off. Now there's no situation here where I'm going to be applying a negative voltage. That's just not a thing, is it really, in this situation? Because it's an ARM chip or an AVR. This will be running on 3.3 volts. So this one here is not actually going to be a thing for us. So that's not relevant. So you can see very quickly which one of those I'm going to want, can't you? And I'm definitely going to want an N-channel enhancement type FET. And then you essentially go to Farnell or RS or any of the other distributors, or look in the drawer, DigiKey at MakeSpace. There's a load of components. If you're ever in there, anyone, at the electronics bench, I think on the left-hand side, there's a rack on the wall. At least there used to be last time I was there. And you could have a look in there and you could probably find some transistors that would do the job. We could, if we wanted, actually, let's go and just wind ourselves back since we're on this subject. And just trying to find the circuit for, here we go, for this one. So, tell you what, let's just rub everything out here, shall we? And work out. From our handy cheat sheet, there we go. Right, so just going to rub that out. Right, so on this one here, what we want is, if we think about it, so the gate source, so that's this one, this voltage here. So this is always going to be at 0 volts, this end here, usually. So if that's at 0 volts, I'll make sure I get this the right way around, which one we want. I think it's going to be, I think it is, if that's at 0 volts, I wish I'd never done this, aren't I? And we want that to be V in. Yep.
Oops, can't see it.
Oh, yeah, back on page, I realised that. So we want that to be V in, and that to be 0 volts, in which case we want this thing to be on. In order for the source to be the same as the input, we actually want this device to be on. Yep.
Right.
Yep. So we want it to be like a switch. We want it to be on.
Yeah.
So the gate source is going to be a negative voltage because the source is larger than the gate. VGS. 0 volts minus V in equals minus V in. That makes any sense? Right, so let's have a quick look. So let's just have a bit this way so we can all see. There we go, right. So we start trying to knock some of these off on our cheat sheets. So minus V in, we want it on. So it's going to be that one, isn't it? Negative voltage, we want it on.
Yeah, that's the only one.
Well, it's the only one, but we can convince ourselves just in case. So let's say, like an idiot, we plug in the battery the wrong way round. So this is then at V in. Well, we want that to be 0 volts because our circuits are microcontrollers attached to this point. So we definitely do not want to have any power running to our circuit. So we want it to be off, don't we? So if it's the right way around, we want it to be off.
Yeah.
So there we go. So we want the P-channel enhancement transistor. And would you believe it? That's a P-channel enhancement transistor. I just happened to put the right one on. And that will work every time.
Great. Matthew had a question for you as well.
Yeah, so the microphone's not working for people. I'm sorry if they're not, but yeah, if any questions, I'll just look in the chat here as well and see if I can find something. I prefer the microphones to be on. Let's say my video's off as well.
I can read the chat.
Oh, here we go. Going back to the power boost. I can see and hear you, that's nice. I'll go, okay, with the BJ op amp, could you go over why both transistors and the op amp are required? Yes, okay, let me go back, Matthew. Let me just find it. Here we go, right. It's good for me to look in the chats. So, okay. Hopefully the message isn't sitting across the, move that out of the way. So, any questions here? Going back. Yeah. I don't have a mic. Right, okay, so, right, let me just go over this again. So why have we got both? Right, let me recap for us. So it was just an example, to be honest with you, just to try and illustrate the use of an NPN transistor. So let me go through this again for us and add a bit more detail. So let's say you did have an op amp outputting a driving something. If you look at most op amps, typically, depending on what you buy, but they may have a maximum current drive capability. Some of them could be just 30 milliamps. Some of them might be less, some of them might be more. It's certainly not going to be in the amps region, and it's unlikely to be in the hundreds of amps, unless you bought a power op amp, of course, I suppose. Whereas we might have something we want to drive that requires a lot of current. Let's say, for example, we have something that wants to drive, let's say, 3 amps, for example. Let's just assume that what we're trying to drive requires a lot of current. Now, in this example here, there's no way an op amp is going to be able to deliver that sort of current. So one way to solve that problem is to use a transistor in this sort of arrangement. This one here we had at the beginning, which is a 2N, I'll write it down here actually. This 2N5301, for example, which I bought, it's quite large and chunky. This one, for example, is capable of driving up to 30 amps through it. So it's more than capable of delivering the current you want. But the current I want, my op amp or my computer in my microcontroller clearly isn't able to deliver that sort of power. You could, quite possibly, if you were driving a microcontroller, you could obviously, this could be your microcontroller, of course, instead. Just the example I chose. So I hope that answers the question, Matthew. Let's go back to chats here today. Let's see. See what else we've got here. Yeah. So hopefully, Matthew, that answers that for yes, thank you. Sorted, good. We're here for questions. We've got anything else here? I can see I can hear you technically. Oh, that was me earlier on the desktop. Okay, well, that's all. That's the only questions I've got. Everyone's very well behaved. Does anybody want to add anything or any comments? Otherwise, I will start to wrap up for us today. I mean, there is a ton more stuff on transistors. You know, if you have a look around, you'll see there are things called IGBT, which is current gate bipolar transistors. So there are so many different options. There's things called Darlington pairs. I could show you very quickly a Darlington pair. Things you can do. If you take this one here, we've got a couple of minutes. I'll just share this with you. Why not? So something else that you can do with transistors. I'll be honest, I've never ever worried about doing this, but it's certainly something you can do if you felt so inclined. Going back to the original early transistor we spoke about, where every transistor has called an HFE, which is the ratio between the current through the collector and the current through the base. And if you remember, what I did say is every transistor has a HFE value, but it's never fixed. It's fixed for the transistor, but say for this one here, this 2N5301. If I got another 2N5301, the HFE might be 50 and this one might be 60, so it would actually be worse than useless. But as a Darlington pair, you could, if you wanted, actually connect them all up. This is called a Darlington pair. So we've actually, so this is then the base, collector, and emitter. So in this one here, that's that's IB, and this is IC. But IB here, IB, I, what was IE, was E dash, IE dash. Make sure I get this right, actually. Or the base, actually, yeah. So the current flowing through one transistor is actually amplified. So you've got two HFE, you've got HFE1 and you've got HFE. It's an easier way to explain it. So you've got two transistors with two HFEs, and combined, they're just HFE1 multiplied by HFE2. So you can get an even higher current gain. But again, because it's so unique per component, you just don't really know what the value is. That's called a Darlington pair. As I say, there's so many different ways you can use transistors, which is why I think they're fascinating things. And say, just to recap. Yep.
Sorry, could you just write Darlington pair next to
that?
that?
Yeah, absolutely. I imagine it's invented by Mr. Darlington. I could have looked that up. There, Darlington pair. That's how it is.
Lovely.
So yeah, so there's so much more you can do with transistors. So we just haven't got the bandwidth to cover everything. But what I have shared with you this evening are the sort of things I use them for. You know, certainly I use them to protect my circuits. I use them quite a lot for voltage level shifting. We saw the NOT gate. Always use them for turning like motors and say buzzers on and off all the time. Do I often use current gain? Very rarely in sorts of microcontrollers that I'm designing, if I'm honest with you. As I say, yeah, for a lot more background information, just going back there, Kavita Mara, write that down if you're interested. And there's a few books on, so they're only £5 each. I thought they were really good value for money. I really did when they arrived. He's got one, this was called Bipolar Junctions, and this one's called FET. If you want the complete set, he's got one here on PN junctions for diodes as well. So there's a ton of background stuff in there. So you know what, 15 quid? That's a lot of background information for you. So I'll just wrap up then for everybody by saying that the next show time next month is Wednesday, the 1st of December. And we're sticking with the theme of microcontrollers, which is for this whole season 2. And we're going to have a look next time, just coming back to these, we're going to come next time, the communications on these devices, on all microcontrollers, if you want to have a look, is called, I'll write this down actually for you all. Next one is, that's right on the back. It's easier. I2C, we're going to look at next time, which and one called SPI. So these are 2 standards for next time. They've been around since the 1980s. They are on every single microcontroller, microprocessor without fail. I would say as good as damn it, 100% of devices that you connect to microcontrollers will have one of these 2 interfaces. I think I2C was invented by Motorola, I think something like 84, 86. And SPI was their answer to it, called Serial Peripheral Interface or Integrated Circuit. This thing was Philips, and that's Motorola, or was the other way around. I'll make sure I've got that right. So next time, we're going to dig into these 2 communication protocols. As I say, all these notes are all available to download. So if you haven't downloaded them, you can just pop onto Silicon Cortex, downloads. If you scroll down to that section, hit the icon, and you'll be able to download last month's, this month's, and all of last year's. They're all there to download. So apart from that, everyone's been really well behaved tonight. Sometimes I get tons and tons of questions and lots of comments. So hopefully I have shed a little bit of light for people. Oh, there's a couple more questions. Let me just check just before we close. Thank you very much. Useful and interesting. Good. I've enthused at least one person, Deb. That's what it's all about. Just one person. That's all I'm after. Just to help one person at least, and I'll be happy. Right, I think it's time for tea. If no one's got anything else.
No, that's fine for me, thank you.
Okay, brilliant. And the camera off me clearly didn't work today. I don't know why, but you know, you got my radio show voice and lots of pictures. So I'll sign off there with you all. If I do stop sharing there. And I will see you all next month for some fun and games with more chips. So we'll hook some stuff up next time to a computer, and we'll get some data coming off chips. Maybe we'll look at temperature. That might be a good one for us to look at.
Okay, that's lovely. All right.
Thank you, everybody. Thank you.
Bye.
And I will see you all next time. Thank you. Bye for now, everyone.
Bye.